All right, so it's been a couple of minutes. What's a good antiderivative for this function here?
1/2 natural log of x squared.
This is actually not going to be a natural log. So if I had a function where I had the numerator was the derivative of the denominator, then that would be the case, but this one's not going to yield a natural log.
For this one, I got x to the power of -3 divided by -3.
So sounds like you try to do power rule, but I think you might have gone the wrong direction.
Just 1 over x.
What was that again, Ben?
Just 1 over x, right?
Close.
Negative 1 over x, excuse me.
Right, -1 over x. -1 over x plus c. Or if you want to think about it in terms of power rule, x to the -1 divided by -1.
Yeah,
really
I accidentally did the wrong direction.
Yeah. Yeah, I think
plus
Mark is supposed to
minus.
keep that a derivative. So really what I'm doing for all of these is just evaluating -1 over x from 1 to 2, which should give me what?
That would be 0.5 according to GC.
Yeah. So let's try to do it by hand. But so yeah, -1/2 minus -1 equals 1/2. And really all these are gonna come from that same antiderivative. So how about if I integrate from 1 to 100?
I got 0.99.
Yeah, this should come out to, so I'll go ahead and skip some steps here, but basically should come out to -1 over 100 plus 1. So Mark says 0.99, which is the same as 99 over 100. So maybe now we can see a pattern here. What is this guy going to be?
That guy I got 0.999.
Yep, 999 over 1,000. And just because I'm curious, if you're using GC, was it able to handle this one?
Yeah, I got just 1 for that.
Okay.
You were able to enter infinity in the integral in GC? I didn't know you could do that.
I just said f of infinity minus f of 1. And in order to type in infinity, you just say INF.
Okay, good to know. Thanks.
So let's look at the way we've been handling this antiderivative, though. Basically, what I've been doing is this. This would be -1 over infinity. But that might be hurting some of your eyes right now. Is it okay for me to write that?
I mean, like that doesn't really make sense. Like I've never seen a function like that.
Isn't that just 0?
I mean, so Mark is getting a value on this integral from GC of 1, which would lead you to believe that this first term is effectively 0. And we'll see that that ends up being the case, but really writing things like, you know, the cardinal sin in math, if you're ever writing down infinity like it's a number, you're doing something that's not totally okay.
Don't you need to throw a limit as something approaches something somewhere in there?
That's what we're going to get to. So, but hold that thought about that integral having a value of 1, the integral from 1 to infinity of that function, because I'll spoil it for you right now. That is the value of the integral, and it is possible for us to evaluate even with that that upper limit being infinite. So let's make some conjectures here. I have this integral 1 over x to the power of t. T is some unknown constant. For what values of t do we think I'm going to get an actual value? So obviously we know that, I mean, I've kind of spoiled this, that when t equals 2, we get a value.
It's
so let's make a number line here.
This is basically a p-series, right?
Does anyone else see that similarity to a p-series here?
Just about.
Okay, so let's throw a 0 in here. we know that 2 is part of our, so whatever range of values we decide that this is going to converge for, we got to include 2. What else do we think? Let's use 2 as a jumping off point. If I do something bigger, like let's say 10, do we think that will have a value?
Yes.
Yes.
So, and maybe, you know, so far I've only heard one person mention the p-series, but I'm hopefully some of you are seeing that similarity here. And if we're going on with the assumption that this is following a p-series or analogous to a p-series, when is this, you know, basically I'm filling in, I'm bolding in all these convergent values. How low can I go until that behavior stops, until I'm no longer converging?
Well, any value greater than 0.
So I got 1 vote for any value greater than 0. So I'm going to put like a parenthesis in here to show that I need to be strictly greater than 0.
Are we talking about the series or the sequence?
So that's a good question. We're talking about, you know, sequence versus series. Think about what an integral does.
Well, isn't the integral like a sum of like all the individual numbers? So it's like a really big series.
Yeah.
basically?
So, and I think we haven't really talked about this in class or in recitation directly, but I've had a few people ask this question, and you know, there are some pretty clear and not coincidental similarities between integrals and series. Let me just draw a basic graph here. So let me show you what, just a rough idea of what this graph looks like. So if this is x equals 1, then basically this graph is going to look like this. So when we're integrating, we're dealing with continuous functions. I care about where this, what this function is for every value of x. But for a sequence or a series, I only care about the values at certain places. Where do I care about those values?
Natural numbers usually.
Yeah, just basically I'm sampling. So every so often, I care about what the value is. So with a sequence or a series, I'm getting those values from this function, but I'm only picking out, you know, I'm picking out a specific ones of them. So all that to answer the question, if I look at an integral, am I, you know, drawing a comparison to a sequence or a series? What do you think is more appropriate here? Should I be treating this as something related to a series or a sequence?
The series.
Series.
Should be a series. Yeah, I mean,
I agree with Ben.
yeah, so think about what an integral does. I mean, the way we built up integrals, and in fact, if you want to go to like, you know, day 1 or 2 of the lecture for this class, you will see that, you know, the way we built an integral was by starting with a series and then just making the sums infinitely close together. So yeah, they're very closely related. So having said all that, what values of t do we think are actually okay?
Well, we know the harmonic series diverges, so
Okay.
1 wouldn't work.
So we know that 1 wouldn't work, assuming that this thing acts the way a p-series should.
Yeah.
So 1 doesn't work. So we know 1 doesn't work and 2 does. So where do I draw that dividing line in here?
I'd draw it at 1 as an open interval.
Okay. Let's go with that.
Wait, so 1 doesn't work for what?
So yeah, that's a good point. I'm not being all that clear. I'm basically, all of this filled in red right here. These are the values of t where integral converges.
And the exercise at the beginning was showing us that when t equals 1, we get infinite. No, t equals 1. It was
No, so what was the value of t that we did in the last slide? It wasn't 1.
Was
It was
9?
2.
It was 2. It was I gave you 1 over x squared.
Yeah, that's right.
So yeah, t is, I think you might have got that and confused with the lower limit of the integral. When really, if you want more details, I can kind of get into this if we have time, but really, so long as I make this lower limit positive, this is all going to be, the convergence is going to be the same. You won't get the same value, but it'll converge or diverge regardless of what this value is. All right.
Is it strictly positive or is 0 okay?
0 is not okay. Why not?
Because it'll be undefined.
Right. You can't define this function at 0. And I think you all have already answered this question. Does this look similar to something you've seen recently? And we've kind of been talking about it as the P series, and yeah, there's no accident there. So let's talk about the P series test here. So I'm actually going to integrate this from 1 to infinity. So the way we do that is I'm going to treat this like a limit. So I'm going to integrate from 1 to b. And I really need to put my limit operator in there if I'm going to talk about it as a limit. The limit as b approaches infinity of the integral from 1 to b of x to the negative t, not dt. dx. T is a constant. So I'll go ahead and write down that antiderivative. Really, this is not going to act any differently than x squared did. So I'm going to take my power, I'm going to add 1 to it.
And incidentally, before I start scribbling down in parallel, can we get a copy of this slide?
Yeah, so I'm recording this. So I'll go ahead and admit to you, I have never annotated on slides like this before. So I don't know if the slides are going to be savable like this, but I will certainly post the videos.
Thank you.
So just basic power rule, add 1 to the exponent, divide by the new exponent. And then I'm going to evaluate this thing at b and 1. Everyone with me so far? Okay, so now I still want to evaluate this limit, which I am so used to calling this t, but really I want to call it b. The limit as b approaches infinity of, let's separate some things out, 1 over t plus 1 times x to the negative t plus 1 with b to 1, or 1 to b. And now that I have this integral, I can follow the
Why is it -1 over t plus 1?
so over here, so my exponent was negative t, right?
Yeah.
So basically I'm dividing by negative t plus 1.
Oh, I see. Okay.
Yeah.
Gotcha.
Actually, did I do something? Oh no, this is fine. Yeah, I just instead of keeping the negative sign in the denominator, I just moved it out in front. All right, so now I'm actually going to plug these things in. So -1 over b plus 1 times x to the negative b plus 1. No, why am I plugging things in for b, guys?
If you're evaluating it, don't you have it for b and then?
Yeah, so I keep plugging things in for the wrong variables here, but we'll get it back. And then subtracting that, I want to plug in 1 for x. So plugging in 1 for x here, that's just going to make that positive 1 over t plus 1.
factor out the 1 over t plus 1?
You can do that. In fact, 1 over t plus 1 is a constant, right?
If t, yes.
Yeah, I mean, so this limit is all about b. So I can definitely pull that 1 over t plus 1 out of the limit. This becomes 1 over b. And this should be t minus 1. And then plus 1. So now that we have this, I'll go ahead and stop here. Is everybody okay with how I've developed this? So basically what's going to happen is this: b is going to get very, very large. What values of t is that going to converge for? What's going on in the chat? Are we missing a negative? Jillian, where do you think we are? I don't think we are.
Sorry, I was just thinking if we're pulling out the factor of 1 over t plus 1, the first one
Yep.
has the negative in front of it.
That is a good catch for sure. Yep.
Sorry,
catch.
I was slow.
All right. So basically, this one is not going to be affected by the limit. This term will be. So basically, I want to know what, as b gets very large, what do I need to be true of t for this term right here to basically vanish?
It needs to be greater than 1.
It needs to be greater than 1, right?
Yeah.
So let's just go with 2 again. If I put, let's say b equals 2, then what I have is this. Negative 1 over 2 to the t minus 1 plus 1. Did I do the wrong variable again? I did. So this is going to come out to be, basically, in this case, it's kind of strange, but we're looking at, even though we did all this starting with an integral, now we're just kind of looking for, so this is the sum. This is the value of the series, this thing contained right here. So I am looking for this thing to just, I want this to go to 0. So now you can kind of look at it as I'm thinking about it in terms of a sequence. I want this term right here to vanish. So as b gets really, really large, is this term going to go to 0?
It's always going to just be b to the 2 minus 1 is going to be 1. So it's
Right.
So yeah, it's always going, b is just going to get larger, and then the fraction as a whole is going to get smaller.
Yep.
Add 1 onto it, it's just going to become 1.
Yep. So yeah, this negative 1 over b, this is, 1 over b, we know that goes to 0. So we know when t equals 2, that we're going to converge. And remember, keep in mind what we're doing here, we're just developing the p-series test. So hopefully the punchline should already be something familiar to you. Really what you want is, I need t to be greater than 1. And that means the integral converges.
It converges to 1 because
No, so that's kind of a tricky thing. And one thing I want to point out, because I don't know if everyone's noticed this yet, so much of what we've done in the last week or two has been to answer one question: does the series converge or diverge? And in most of those cases, we're not asking when it converges, what's the value of the sum? Because that's actually that's a more difficult thing to get your hands on than it seems. What's the only case really where we have a way to find out what the value of that sum is?
The geometric series.
Geometric series, right? And this is not going to fit that model. So we know this sum is going to converge. We don't necessarily know what it's going to converge to, unless you can integrate it and have some kind of idea with that. So any questions on what we've done so far?
Yeah, I have a question. So like, we can see that it converges because of like the outside term as well, the 1 over t plus 1, because that goes to 0 as well. T plus 1 gets bigger and bigger, right? Okay, so like since the whole thing becomes 0.
Really, so this 1 over t plus 1, you know, as long as this t is not equal to -1, we're going to be okay. Because we are taking the limit as b grows very large.
Right.
So t is not really going to affect us. It's really all about the value of b.
Oh, okay.
So really all I need t to do is prevent me from being undefined somewhere.
Okay.
And just to kind of highlight that dividing line again, if I were to put 1 in here, I would have -1 over b to the 0.
Right.
All right, anything else on this? Basically, hopefully this conclusion is not throwing anybody.
So basically, we just proved it.
Yeah, basically this is, I mean, I think Mark used some good examples to show you why the p-series test has the boundary that it does, but this is, you know, one way to justify it. So now we can actually do some improper integrals. So I'll walk you through at least one of these, and then we can, I'll let you handle a few more. So
Is an improper integral one that's got an infinity in it, or
yeah, basically an improper integral doesn't necessarily have to have infinity in it, but it is going to involve you having to take a limit, because basically handling it directly would, you know, basically make you write down something that's not going to be a number. Like I said, for this one, you know, the antiderivative you can do pretty easily. But if you just start plugging in infinity to stuff, you're treating infinity like it's a number, and that's, you know, it's not. So first thing, what's a good first thing to do to handle this this integral?
I was thinking we could rewrite it so that it's 3 times x plus 4 to the -3/2.
Good. All right. And can we take that antiderivative?
yeah, it's going to wind up x plus 4 to the -1/2 and clean up the mess.
Okay. Before we go any further, let's do this. Do we think this is going to have a value? Do we think it's going to converge?
Yeah, it's
Yes.
great.
Yeah, it should, right? So I mean, if we're treating this as something analogous to the p-series test, what's our p-value?
3/2.
3/2, which is greater than 1. So if our conclusion was correct, we should definitely get a sum for this. Divided by -1/2, evaluated from infinity to 2. So now we're going to have this. Now that we've taken the antiderivative, we got to throw in this limit operator. So we're going to do a limit as b approaches infinity of -6, and probably makes sense to rewrite this now, -6 over the square root of x plus 4, evaluated from 2 to b.
Wait, how do you get 6?
3 over -1/2.
Oh. But how does... Oh, okay, so you multiply by 2 to get negative.
Yep,
Okay.
there you go. Yep.
-6 over...
So from here we get -6 over, don't forget that limit operator, the limit as b approaches infinity of
How do you get 2?
How do I get 2?
Oh, that's part of it. Okay, never mind.
Are you talking about the limit too?
Yeah. Okay.
Yeah, that was just given to
And
you.
why do you replace infinity with b in the?
Because I'll give you an example here. Typically, what you do is, when you're evaluating an integral, you would just plug in the limits, right?
Yeah.
But I'm not allowed to treat infinity like a number like that. I can't just say infinity plus 4. So I have to treat this like a limiting case. So I'm bringing in this new value, this new constant b, or you can call it a variable. And basically, I want to know what's going to happen as I let this thing trend upward toward infinity.
And you just pick B because you're not using it anywhere else in the problem. The same way
Yeah,
that-
I mean, you can call it whatever you want. In fact, one reason that I kept making that mistake on that last slide is because literally every other time I've done this, I've called that value t, and Mark asked me to avoid that. So I'm trying to deprogram myself to some degree. All right, so I plugged in b. Now the other one I'm going to plug in 6, so that's going to be plus 6 over the square root
But
of
why is it plus? Oh, no.
minus negative. Good. All right, so now, what do we think about this thing on the left here? What's going to happen to this as b gets very, very big?
It's just going to keep on getting bigger. The bottom,
What's going to keep on getting bigger?
the denominator.
Which means what's going to happen to the overall term?
It's going to go to
over square root of 6.
like -6 over infinity, essentially.
Which is, how can I?
It's going to be a
like, yeah,
really small number.
Which I can, so yeah, it's going to keep getting smaller and smaller and smaller. And if I could do that infinitely, it would go to what?
0.
0.
0. And 6 divided by radical 6 comes out to radical 6. So our conjecture was right. We do have a convergent integral here, even though we're integrating it for every x value to the right of 2. Even though we never stop that, we do have a convergent sum. Any questions on this guy?
Yeah, did you get just rad 6 from -6 plus 6? Just to make sure.
No, here's what happened. Basically, what I did is this. I know that 6 is equal to the radical square root of 6 times the square root of 6.
Yeah.
So if I divide it by square root of 6.
Oh, gotcha. Okay.
Yep, that's what I did there. All right, any questions about this before I move on to another one?
So can we confirm that this converges to rad 6?
Yes, the sum, the value of this integral is radical 6.
Okay.
Yep.
How is this, my bad, how is this different from, so the last one does not converge to 1? Can you,
Oh, so
can you just explain why this converges to rad 6?
Yeah, let me
why
go
the
back.
last one didn't?
Oh, so the one that I did before with the variable t in it?
Yeah.
Yeah, so we were just trying to see for what values of t this limit actually would exist. But now that we have done this proof, essentially, if you fix a value of t, you can make t equal to 10, then you could find the value of the integral. And in fact, that would come, basically, we've already done the real hard work. Really, if you plug in any value of t to this, your limit is going to be given by it'd be basically 1 times 1 over t plus 1.
Okay.
So, I mean, we basically did find the sum in a very general way.
Right. Okay.
All right, so now I got this new one, so from negative infinity to -3 of the integral of 1 over square root of 8 minus x. Do we think this will converge?
Still a positive.
Yes.
Okay, I got to vote for yes. Okay, let's see. So I'm going to swap out my negative infinity with, I'm going to call it negative b. But really, you could call it positive b and just make b go to negative infinity, but A lot of different ways to go. I'm also going to put a rewrite in here. So what would the antiderivative of this expression be?
Square root of 8 minus x and clean up the mess.
Okay, so 8 minus x to the 1/2 divided by 1/2. So that's going to come out to 2 times the square root of 8 minus x, and evaluating that at -3 and also at -b. Do we want to change our votes, or we still think this is going to be a sum?
I'm wondering if that starting from -infinity is going to throw a loop here.
Okay, so I kind of skipped some of the simplification here, so I'll make sure that everyone's okay with this. Also, to make sure I'm okay with it, check me for any mistakes there. But are we okay with this expression here? Okay, so clearly 2 times radical 11, that's going to be finite. What's going to happen to this term over here as b gets very, very big?
That's also going to get, well, negative infinity, going to go to negative infinity with that -2.
Well, keep in mind here that the way I set this up, I was going to -b. So I called my lower limit -b, and I'm letting b go to negative infinity, or sorry, b to go to positive infinity. So those 2 negative signs will cancel out. My radical, the term under my radical here is 8 plus b.
It's going to grow arbitrarily, however big you want it.
Right. So that means this thing cannot converge. And should we have known that before we got started? Jillian is saying -1 is less than p, which is less than 1. So yeah, p falls between that range. But what do we need? What do we need to be true of p for this integral to converge?
Has to be greater than 1.
Greater than 1. And what's this p value here?
1/2.
Positive 1/2. So yeah, we should have expected this to diverge.
The sequence converges, but the series diverges.
Right. And since we're interested in the integral, then that's gonna follow the behavior of the series. So let's look at this one here. All right, I'll let you all tell me how to start this thing.
If we're worried about the limit, do we care about the 7x plus 12?
We are, because I am not solely asking, will this converge?
You want to know what it converges
I want to
to.
know what it converges to, which means I can't just throw things away. So it sounds like, if it was just 1 over x squared, let's talk about that for a second. If I had the integral from 0 to infinity of 1 over x squared dx, let's do one small thing here. Let's make that the integral from 0.1. Would that converge?
Yeah.
Yeah, hopefully you remember from the very first slide that that'll converge. That'll have a sum. Would adding 7x and 12, what would that do? Would that also converge?
Just converge to a slightly smaller number.
Right, because, and what test that we've already talked about are we kind of using there?
We're comparing it to a p-series.
Right, so you're using the comparison test for the p-series. So yeah, you thinking about that, it sounds like we're drawing the conclusion that we expect this to converge. So let's make sure that it does. So how can I handle this from here?
Does this one gonna this is gonna factor, isn't it?
It is. So I think that's a good first move. How does this factor?
Be x plus 4 and x plus 3.
X plus 4, x plus 3. So let's put calculus to the side for a second. I'm not worried about the integral. Let's break this into partial fractions. So 1 over x plus 4, x plus 3 is going to be equal to what?
Just split a line right down the middle. And
Yep, so yeah, this one, there's no special cases or anything. 2 linear factors, nothing repeated. And then I multiply through, and I should have 1 equals a times x plus 3 plus b times x plus 4. And now I'm going to show you something that might make you mad that it was not taught to you before. In order to solve for the a and b here, I'm gonna make x equal to something strategic. If I let x be equal to 3, then I have 1 equals a times -3 plus 3 plus b times -3 plus 4. And that gives me 1 equals b.
And then you're going to do the same thing with -4.
Yep. So yeah, so long as it, and why am I picking the values of -3 and -4?
Those are the zeros.
Yep. Basically, if I can wipe out one of these, it makes it really easy to solve for the other. So I just do that a couple of times.
And even if it's more complex than this, if you can whack out a few of them that way, now
Yeah.
you've got knowns you can plug into the more complex system of equations.
That's exactly right. So yeah, I don't think anyone likes solving systems of 3 or 4 variables in 3 equations. So yeah, if you can give yourself a little bit of a head start. So from here, I should get a equals -1. Any questions so far? Okay, so
Why didn't you show us this earlier?
I take that direction from Mark.
You did drop some hints in the way that you solved the
Yeah,
simple problems.
yeah, and yeah, and I'm not sure why he doesn't use this method, but I don't know if it's a huge time saver, especially with the ones that like Ben alluded to. If you're solving for 3 or 4 constants, you can't get them all this way all the time. All right, so from here, now we can go back to doing the calculus. I want the limit as b approaches infinity of the integral from 0 to b of which one's the positive going to be?
The positive is going to be x over 3.
Yep. So 1 over x plus 3 minus 1 over x plus 4. All right, and those, what is the antiderivative of that expression going to be?
Couple natural logs.
Couple of natural logs. So what's the first one going to be? A natural log of what?
Absolute value x plus 3.
And the other one's going to look very similar. All right. Do we think this thing's going to converge?
No.
I got to vote for no. It certainly looks like it's not going to. But one thing that I want to remind you of, and this might be, hopefully this looks familiar, but it might be a while since you've used it. Are you okay with me doing this, the natural log of x plus 3 over x plus 4?
Oh, logarithm identity.
So yeah, hopefully there's something you remember, even if you haven't used it in a while, that you can do with logarithms where, yeah, the natural log, or so as long as the logs have the same base, which they do, log of a minus log of b is equal to log of a over b. Now do I think this is going to converge?
Yes.
So yes.
So now, yeah, now it seems a little more obvious. I mean, granted, it looks like this is going to go to infinity, and this is going to go to infinity. Then you have infinity minus infinity, which I have no idea how to predict what that's going to do. But if you put these logarithms together, then. So what's going to happen to this fraction as b gets very big?
It converges to 1.
So yeah, this rational function right here will converge to 1. So now let's evaluate the limit. So that's going to be the natural log of 1 minus the natural log of 3/4. What is the natural log of 1?
It's e, isn't it?
Not quite. So remember what the natural log of a number basically is. So the natural log of x,
0.
it's going to be 0. So basically the natural log of x is equal to, log base e of x. Basically what this is saying is this. Basically, the natural log of x is, what power do I have to raise e to get x back? So what number do I have to raise e to get 1?
0.
Same thing you have to raise any number to get 1, which is 0. And I'll remind you of one more thing about natural logs that you might have forgotten. We okay with that, or should I explain why that happened?
Sorry, it might be a dumb question. How did you get 4 over 3 instead of 3 over 4?
So that's absolutely not a dumb question. Basically what's going on is this. You might also remember this from a long time ago. If I had x times the natural log of, 5, that is the same thing as the natural log of 5 to the power of x.
Okay.
Which means this is the same thing as the natural log of 3/4 to the power of -1.
Okay.
And basically anything raised to the power of -1 is going to give you its reciprocal back.
That makes sense.
I'm with you, Kevin. I forgot all my log rules too.
Yeah, I mean, I think it's probably, I don't even know how often they come up in Calc 1, so it's probably been a bit.
Have to brush up.
Yep. Any questions on this one here? All right, I think I have one more, but I think I'll do this. There is a quiz. I'm going to go publish it right now. What I suggest is this. I think if you want some independent practice, this is going to be a good one to do here. So this one, P-Series is not going to give you a good way to make a guess on this, but you can still do everything we did today to help you figure out if this thing converges or diverges, and if it converges, what's the value of that sum. So what I'm going to do is this. I am going to stay online. I'm going to go publish the quiz, and I highly recommend that you work on this one before you take the quiz. but I'll stick around if anybody has any questions.
So is this in general how you go about solving improper integrals, that you replace the funky thing with some variable and evaluate the limit?
Yep.
And the p-series with the example was just to help ground us.
Absolutely, yeah. I mean, and Edward's asking if we have a quiz. Yes, you do. Am I still sharing, by the way?
Yep.
You are.
Okay. All right. So, and good news, I was able to keep those annotations, which is a surprise. So you can probably see me awkwardly trying to go to Canvas so I can publish that quiz. But yeah, if you haven't already, take a shot at this example number 4 here.
You want? I'm guessing the quiz is due tonight, since you want us to do this example.
Tonight, yeah, I left it open until 11:59.
Thank you.
Thank you.
Thank you, Steve. Have a good one.
Thank you.
Oh yeah, I also want to say thank you for sending that email about the vaccine info.
Yeah, of course.
Oh yeah,
I mean,
thank you for that.
I have definitely learned the hard way what happens when you're just a little bit late on that information. So when I found out that teachers were eligible, I did not assume that that included me because I don't teach on campus and I only teach a day a week. So I found out like 4 o'clock that afternoon that I was able to sign up, and my first appointment was at 3:30 in the morning because that was the best I could do. So yeah, if you're interested, I would definitely encourage you to be proactive about it. They fill up quick.
The one thing I haven't seen is the time that they're going to actually open it up. I just saw Wednesday, but I
I
haven't
believe
seen
it's 8 a.m.
8 o'clock on Wednesday.
Yeah.
Mhm.
Of course, that's when the server's going to melt down.
So you should probably wait
mean-
until like 8:30.
I have not. So I have signed up for myself and a few other people in my family, and I have never had that website crash on me. So I think they can handle the traffic. I'll just admit to you that the website is a little clumsy.
Oh,
So-
is it ever?
Have patience if you try to use it. All right, so quiz should be published. All right.
Thank you, Steve. Have a good day.
Thank you.
So I have a question.
Mhm.
It's about like when you would divide by the exponent, I think when you were finding the antiderivative.
Okay. Is there a specific example you want to look at?
Maybe the one where you divided by 1/2.
Divided by 1/2. I think that was. Yeah, okay.
I just kind of don't understand why you would divide by it.
So that is a. Can I still annotate? Not really. Okay. So let's talk about this in terms of derivatives. So if I had x to the, and we're just looking at the exponents, let's do that. If I was going to take the derivative of x to the 1/2, what would that be?
1 divided by 2 times the radical of x.
Okay, yeah, so I think that's eventually what's going to be, but yeah, let's build it up a little bit. So 1/2 x to the negative 1/2, right?
Yeah.
So let's just keep it there because what I want to talk about is this. When you take a derivative, the first thing you do is multiply by exponent. And then the second thing you do is replace the exponent with exponent minus 1. So are you happy with that 2-step process there?
Yep.
So when you go the opposite direction, now I'm going to take x to the 1/2 and I want to do an antiderivative of it. So antiderivatives and derivatives, if it's, yeah, I mean, they're called that because they're inverses of each other. So I want to take this two-step process and I want to do the steps in the opposite order, and I want to do the opposite of them. So how would I take the antiderivative of x to the 1/2?
You would divide by the exponent and add the exponent by 1.
Opposite order. So it would be x to the 3/2 over 3/2. Because so basically I want to reverse these steps and also do the opposite of them. So instead of taking the exponent and subtracting it by 1, I want to take the exponent and replace it with 1 greater. And then instead of multiplying by the exponent, I want to divide by exponent.
Okay. That helps. Thank you.
No problem.
Can I ask you if I came up with the right number for your example number 4?
Yeah.
-2 over e?
-2. Let me make sure. I got the solutions saved, and I feel like I had the positive version of that. Yeah, I have +2 over e.
I probably,
So yeah, you got a sign flip in there somewhere. But yeah, I mean, it definitely converges to 2 over e.
okay.
Hey, I just had a quick question. Is
Yeah, go ahead.
the previous lecture going to be posted on your YouTube channel?
The lecture from class, or the one that I recorded today?
The previous recitation about the alternating series, I believe it was.
Oh no, I didn't record that one. Sorry about that.
No, it's okay. Thank you, Stephen. I'll see you
Thank
next
you.
time.
See ya.
So I'm still kind of confused by this.
Okay.
Can you how would you go about doing problem 4? Like just starting it?
Yeah, we can do that. Let me reshare. Problem 4. Okay, so how did you start this?
I honestly have no idea.
Okay, so I'll put it in the limit operator. So what is the antiderivative of this function?
Would it be I know e to the e to the -x over 2.
But because this is not simply e to the x, so there's essentially I'm undoing the chain rule.
Yeah.
So basically this is going to be e to the -x over 2 divided by the derivative of this inner function here.
Okay, I see that.
Okay. Oh. So this comes out to be the limit as b approaches infinity of -2 e to the -x over 2. You okay with that so far?
Yeah, because -1/2 becomes -2, right? Yeah.
Yep.
Okay.
So then it's just a matter of evaluating.
So really, we want to find the antiderivative.
Yeah, I mean, it's an
its
integral.
most basic form, and then then just plug in b in.
Yeah, so
limit.
At its heart, I mean, yeah, taking an integral is the same regardless of what the function looks like, regardless of what the limits are. The only little wrinkle with these is because, I can't just, e to the -infinity over 2. I can't think about that directly. So I just replace it with some value, and I let that value approach the limit that I care about. So
And
yeah, this guy right here becomes 2 over e.
That I see.
Okay, this one right here, I'll go ahead and rewrite as -2 over e to the b over 2. I've been clumsy with my limits. So that first term is really what's holding me back now. What will that first term do as b gets very large?
It would essentially go to 0, wouldn't it?
Right, so yeah, your denominator is growing without bound, so you just get 2 over e.
It'd be 0 plus 2 over e.
Mhm.
Okay.
just help me spot where I flip the sign. Thanks.
No problem.
So essentially, if like for the first part of it, like -2 over e to the b halves, we just want to find the limit of that, right? To make
Yeah,
it
so I mean,
easier
yeah,
to calculate.
yeah, the only wrinkle here is, this every integral you've done before this, at least this semester, you just take the antiderivative, plug in the limits, and that's it. Now you're taking the antiderivative, you plug in the limits, and then you have to think about this limiting case of one of those limits.
Gotcha. Okay, thank you.
No problem. Any last minute questions, Ben? I'm going to sign off.
Oh, I'm just scribbling through the quiz problems, and I figured that I kept half an ear open. Maybe I would learn something, and I did.
Okay. All right. Have a good one.
You too. Thanks much.
No problem.